One of the more interesting features of electrons in molecules is that there are certain circumstances under which they become, shall we say, delocalized. They become spread out over many atoms. This is something that we really haven't talked about before because we've been talking about electrons around atoms or electrons very strongly located within bonds. This means of delocalizing is something that we'll explore in this lesson and in the next lesson as well. And it's a very important one because it's something that we see in a lot of different molecules and a lot of different ions. So let's get started. Our learning goals include how we draw Lewis structures for elements that can expand their valence shell, that is atoms that are in the third row of the periodic table or lower. And then we'll extend those Lewis structures to treat delocalized electrons, electrons that can be spread out over many atoms, because this is something for which Lewis structures really weren't necessarily designed to begin with. Okay, the Lewis structure for ozone is shown here, and you can see that if you were to sit down and write out a Lewis structure for ozone, this is what you would come up with. One might ask, what are the formal charges on these oxygens? Well, we're now equipped to answer that question, but we're then going to extend that to see what we expect the Lewis structure for sulfur dioxide to look like. So what are the formal charges on these oxygens? Well, for this oxygen at the end, remember that is one of the common bonding structures for oxygen, a single bond and 3 non-bonding pairs of electrons. In the middle, we have another one of those standard bonding structures, 3 total bonds with 1 pair of non-bonding electrons, so that has a charge of +1. And then the one at the end is the one that has 0 formal charge. So interestingly, ozone appears to be a molecule where we've got one oxygen with a -1 charge, one with a +1 charge, and one that is neutral. What would we see for sulfur dioxide? Well, remember, sulfur is right below oxygen in the periodic table, so we should expect a very similar sort of Lewis structure, and we might start with something that looks a lot like the thing we've devised for ozone. However, sulfur is one of those elements that can expand its valence shell. So that means that it can relieve that separation of formal charges by forming another multiple bond. Okay, now when we get to this sort of structure, if we look closely at sulfur, it has more electrons than one would normally find based on the octet rule. But there are no formal charges anywhere on this molecule. Now you might say, well, we just learned about formal charges, they must be important for something. Well, yes, they are important, but there are certain cases in which it is more important for a molecule as a lower energy form to relieve that by expanding its valence shell, if it can. All right, now another thing I would note is when we study sulfur dioxide, the bonds in sulfur dioxide are equivalent. And this is one thing that helps justify why we would create that additional double bond. Would you expect this to be true for the bonds in ozone? Remember, oxygen cannot engage in an expanded valence shell, so what we've drawn for ozone is pretty much as far as it goes. Well, this is a conundrum in the Lewis structure thing. When we do experimental measurements on ozone, we find in fact that the 2 oxygen-oxygen bonds are equivalent, just as they are in sulfur dioxide. So what's going on here? Well, it turns out there are 2 equivalent Lewis structures for this molecule. I've drawn one of them, but there's also another one where the double bond is between the first 2 oxygens and the single bond between the second and third. Well, these 2 are equivalent structures, and so they can interconvert, if you will, between one another. And we call them resonance structures. Now, we'll talk a little bit more about this, but the fact of the matter is they are not necessarily interconverting between these. What we're seeing here is a shortcoming in the Lewis structure business. Lewis structures are built to describe localized bonding, but they're not necessarily built to denote bonds that can change like this and create resonance structures. So how could we distinguish between these 2 resonance structures? Well, the fact is we can't. These 2 resonance structures both contribute overall to the molecule that we know ozone to be. So let's define what resonance structures are. They're basically going to be equivalent Lewis structures, 2, possibly more, that represent delocalized pi electrons. And this is an important point. they never refer to electrons in a sigma bond. They always refer to pi electrons, or non-bonding electrons that happen to be in a p orbital. They reflect the same bond connectivity, so we're not going to change how the atoms are connected to one another. They have the same total charge, so we're not going to add or subtract electrons from this. And only the locations of the pi bonds in these molecules, in the two resonance structures or more resonance structures, only those locations are different. All right, now we can relate these by a simple electron movement. So consider this structure for ozone with the second structure for ozone. We could take the non-bonding electrons on the end, move them into that double bond, and that would kick that double bond out and move it into non-bonding electrons. That results in the structure on the right. Similarly, on the right, we could take the non-bonding electrons on the end, form a double bond there, take one of the two bonds in the double bond and make it a pair of non-bonding electrons on the first oxygen, and we would get the resonance structure on the left. So you can see a simple movement of these electrons can connect these two resonance structures with one another. I'm not going to ask you to know how to move these electrons, but I want you to appreciate that these connections can be made, and that in fact this is one way to identify whether or not you have a legitimate set of resonance structures. Can you do a bond and electron movement like this that connect the different structures? Now, what does this look like from the standpoint of where electrons are in orbitals? I want to stress only pi electrons are involved in connecting one resonance structure with another. So let's consider what it looks like in ozone if we were to draw out what these orbitals look like on the molecule. So traditionally the structure that we've shown on the left with the double bond between the second and third oxygen might look like this on this structure on the left, where there's a pi bond between that. Remember that the sigma bonds are still present there, between occupying the region between the atoms, and the oxygen on the left-hand side has a p orbital that contains a pair of non-bonding electrons. Now when we move those electrons over, we're moving it into that gap between the first two atoms, where we're taking the pi bond electrons and moving them over so that they reside solely in a p orbital on the third atom. We end up then with a structure that looks like the one on the right. So this is maybe a closer approximation to what that looks like those electrons are doing in connecting those two resonance structures. And you can see that because we're dealing with movement of electrons between a pi orbital and a p orbital, this can actually be a very facile transformation. And in fact, it is such a facile transformation that we don't really like to think about them moving, but really more an average structure, which I'll get to presently. I want you to pay particular attention that the sigma bonds are unaffected by this resonance. This is always true. If you have a pair of resonance structures where you change sigma bonds, you have the wrong idea. You have the wrong set of resonance structures. So, as I started to say in the previous slide, we can think of these as really representing an average structure. So they don't actually migrate across these atoms. It might be better to look at a picture of these things as an average structure. So here are the resonance structures for ozone again. Here's what it might look like if we sort of created our own variation of Lewis structure for ozone, where instead of putting a solid double bond between one side, or the atoms on one side or on the other side, we basically create a hybrid sort of situation where each of the sigma bonds are still there, and the pi bond is only partially created on either side of the molecule. Okay, this might result in, and again I'm averaging, there's always a +1 charge on the central atom. This seems to be true in both of the resonance structures. But on one case there's a -1 charge on the left atom, and on the other case there's a -1 charge on the right atom. So this averages out so that there's like a -0.5 on each atom. This might look like something like this, where we've got 2 equivalent sigma bonds and 4 delocalized pi electrons. When we draw an MEP surface for ozone, you can see that it looks very symmetrical. This is at least what the best calculational models would tell us. But you can also see that there is clearly a positive lower electron density on the central oxygen atom, the blue region in that MEP surface, whereas there's a partial red or partial negative charge on the two outer oxygens. All right, so this is a more accurate, more realistic picture of ozone, even though it's not something that we can adequately represent using a single Lewis structure. So what are some guidelines for drawing these? First of all, the sigma bond connectivity must be the same for all of the structures that are related by resonance. The total charge must be the same, so ozone doesn't gain or lose charge when we go from one resonance structure to another. The number of single unpaired electrons must be the same. Well, we're not running into this particular circumstance in ozone. It's just something that you might file away should we get to the point of having to consider that. The octet rule must be satisfied by all elements in the first and second rows. This is why ozone must exhibit these resonances, whereas sulfur dioxide does not. Sulfur dioxide can solve this problem by simply expanding its valence shell because it's in the third row.